So, hi everybody, my name is Andreas, and today I'm going to be presenting our work, REIS, a high-performance and energy-efficient retrieval system within storage processing. So here is our executive summary. The problem is that current retrieval augmented generation, or RAG pipelines, incur significant data movement overheads between the host and the storage system. Existing in-storage processing, or ISP, solutions only accelerate the nearest neighbor search stage of RAG and introduce significant area and power overheads. Our goal in this work is to alleviate the I/O data movement overheads of RAG by accelerating both nearest neighbor search and document retrieval without performing modifications to the storage system. REIS introduces a lightweight scheme that links embeddings to documents, an ISP-tailored data placement algorithm, and an approximate nearest neighbor search or ANNS engine that uses the existing components within the storage system. Our key results are that REIS improves throughput and energy efficiency by 15 and 55 times respectively over a CPU baseline. It reduces the I/O data movement overheads of RAG to under 0.2% of the total runtime, and it outperforms an ISP-based ANNS accelerator by up to 2.5 times. So this is an outline of my talk, and I'll start with a bit of background. Typical LLM inference pipelines receive a query, which is then fed to a large language model to generate a response. However, large language models can only generate responses from data inside their training sets and require expensive retraining to memorize new data. As a result, this limits their effectiveness in real-time and domain-specific applications. One solution to this problem is RAG. RAG combines the text generation capabilities of large language models with the information retrieval techniques from document databases. RAG identifies the most relevant documents to the query to generate a higher quality response. To achieve this, RAG first uses an embedding model to generate embeddings for both the query and the document database. In this case, the embeddings are multidimensional vectors representing the information contained in query and the documents. Unfortunately, they can be quite large, reaching 8K dimensions. As a result, the document database has to be stored in the storage system and usually in flash memory. The next step is to then identify relevant document using a process called nearest neighbor search. Nearest neighbor search involves calculating the distances between the query and the database embeddings and then identifying those with the smallest distance to the query embedding. To generate the response, RAG then combines the documents that correspond to these embeddings with the query, feeding them to the LLM to generate a response. The problem, however, here is that nearest neighbor search creates significant data movement and also that the large embeddings lead to expensive distance calculations. To address these issues, researchers have proposed multiple approaches, one of which is quantization, integer quantization or binary quantization or even product quantization, which reduces the dimensionality of the embeddings, making the computation simpler and reducing the size of the database. Another approach is in-storage processing, which employs the computational resources within the storage system and takes advantage of the large internal bandwidth of the SSDs. In our motivation section, we analyze both of these approaches. First, we perform a latency breakdown of all the stages in the RAG pipeline when using binary quantization. As you can see from the figure, dataset loading comprises almost 70% of the total latency of RAG and dominates the total runtime, especially for large datasets. We thus deduce that quantization on its own is not enough to alleviate the data movement overheads of the RAG pipeline. Second, we explain why existing in-storage nearest neighbor search accelerator designs are not suitable for accelerating large RAG pipelines. Specifically, existing designs mainly accelerate the search process, which comprises only a small part of the total latency, but do not provide support for retrieving the documents from storage. In addition, they introduce significant modifications to the design of the SSD and often incur significant power and area overheads, which hinders their adoption. Our goal in this work is to fundamentally alleviate the I/O data movement bottlenecks of RAG through an ISP design that does not require modifications in order to perform computation inside the storage system. To this end, we propose REIS, which stands for Retrieval System within Storage Processing. The key idea of REIS is to leverage both in-storage and in-flash processing to exploit the computational parallelism inside the flash storage and conserve the precious flash channel bandwidth. REIS receives the query embedding from the host system, performs in-storage processing to identify the most semantically relevant document chunks, and then returns them to the host system to perform generation. To achieve this, REIS employs three key mechanisms: an efficient ISP-tailored implementation of the inverted file algorithm, a low-cost embedding to document linkage mechanism, and an ANNS engine that uses existing computational resources within the storage system. However, the design of the storage system creates unique limitations. For example, the embedded cores of the SSD have limited performance and functionality as they lack floating point support. Also, computation inside the flash chips is limited to simple bitwise and bit counting operations, and error correction limits ISP performance due to the data movement overheads of moving data from the flash chips to the embedded processor in order to perform error correction. We base REIS's design on the existing design of the SSD, which is comprised of multiple processors, a small amount of DRAM, multiple flash channels with multiple flash chips each, that are then composed of multiple flash dies. Each flash die contains multiple planes and pages, a page buffer for each plane, and peripheral circuitry, which all contain logic that can be used for computation. Let's now move on to the database layout of our proposed design. REIS creates separate regions for storing embeddings and documents. It stores embeddings using enhanced SLC programming for robust ISP operations without error correction, eliminating thus any data movement overheads stemming from ECC. It stores documents in TLC to provide high storage density for documents, and it stores embeddings and documents contiguously to avoid address translation overheads. REIS links embeddings to documents by storing the physical address of the document chunk in the out-of-band area of the embedded pages, again eliminating translation overheads. Since REIS uses both in-storage and in-flash processing, we employ the inverted file algorithm, or IVF, with binary quantization to accelerate nearest neighbor search. IVF organizes embeddings into clusters, performs a coarse-grained search to identify the nearest clusters, and then performs a fine-grained search inside the clusters to identify the nearest embeddings. The inverted file algorithm provides a good performance and accuracy trade-off, especially with binary quantization, and also features distinct characteristics that make it suitable for the storage system. We design an in-storage ANNS engine that provides support for IVF. For both the coarse and the fine-grained stages of IVF, the ANNS engine copies the query embeddings to the page buffer, moves the document embeddings to the page buffer, and then calculates distances using logic in the page buffer and in the peripheral circuitry. At this point, the embedded cores take over the execution. So, the embedded processor performs quick select to identify the nearest clusters and the embeddings, and in the case for the fine-grained search, it performs re-ranking and quicksort to refine the search results. The ANNS engine then transfers the document chunks from the flash pages to the DRAM and then out towards the host system, completing the retrieval process. We further improve on our design by proposing the following three optimizations. One is distance filtering, which quickly filters out embeddings with large distances inside the flash dies. Another one is multiplane input broadcasting, or MPIBC, which transfers the query embeddings in parallel to multiple planes at the same time. And another one is pipelining, which overlaps multiple flash page reads with distance computations, further eliminating any latency. I will now move on to the evaluation section. For the evaluation of REIS, we use multiple baselines. We use CPU real, which is a CPU-based retrieval system running IVF, NoIO, which is the same CPU-based system but without incurring any IO data movement overheads, and NDSearch, which is a state-of-the-art ISP-based ANNS accelerator. We evaluate performance on exact nearest neighbor search, or brute force, which we call BF here, and the inverted file algorithm, or IVF. We evaluate throughput measured in queries per second, energy efficiency in queries per second per watt, and end-to-end retrieval performance. REIS is evaluated on multiple diverse datasets and on two SSD configurations, SSD-C, which is a cost-oriented design, and SSD-P, which is a performance-oriented design with more channels and higher bandwidth per channel. For their performance evaluation, we compare REIS to the throughput of no I/O, and REIS uses SSDC and SSDP. Throughput is normalized to that of the CPU real baseline, and we evaluate performance on BF and IVF across different recall values. As you can see from the data, REIS outperforms no I/O due to the massive parallelism of the SSD. Also, the performance improvements increase as the recall values increase because that requires more computation, which further highlights the computational capabilities of the SSD. We perform a similar experiment for the energy efficiency evaluation. This time, the y-axis represents QPS per watt, normalized to the same metric for the CPU real baseline. We again make a similar observation, which is that improvements in energy efficiency increase at higher recall values. In the paper, we evaluate these on multiple different datasets, and we observe that the patterns are largely the same, and also that performance benefits increase with larger datasets, again due to the parallelism of the SSD. Let's now move on to the evaluation of the end-to-end performance. We repeat the latency breakdown experiment from the motivation section, this time also performing document retrieval with REIS. As can be seen from the plot, the once almost 70% of latency stemming from the dataset loading and search is now combined into a single in-storage retrieval step that comprises just 0.15% of the total latency. We thus conclude that REIS eliminates the data movement overheads from the RAG pipeline. For my final evaluation slide for today, we have a comparison to ND Search, a state-of-the-art ANNS accelerator design. For this comparison, we normalize the throughput of REIS to that of ND Search running HNSW and ISCA'25, two graph-based algorithms. We evaluate both REIS and ND Search on SIFT-1B and DEEP-1B datasets, and we find out that REIS improves performance by 2.5 and 1.8 times over ND Search when ND Search uses HNSW, and 1.05 and 1.36 times over ND Search when ND Search uses ISCA'25. We attribute this performance increase to the fact that REIS with IVF features streaming access patterns that exploit the internal bandwidth of the storage system. Our paper is available on arXiv, and in the paper you will find a lot more evaluation. For example, a performance evaluation on more datasets, energy efficiency evaluation on more datasets, a sensitivity study on the effects of the proposed optimizations, DF, PL, and MPIBC, and there is also a performance analysis of different ANNS algorithms, which justify our selection of IVF. Let's now move on to the conclusion. So, the problem is that currently RAG retrieval is bottlenecked by I/O data transfer overheads between the host and the storage system. To solve this issue, we propose REIS, the first system for RAG retrieval that leverages in-storage processing using the existing computational resources within the storage system. Our key results are that REIS outperforms CPU search by 15 times on average, improves energy efficiency by 55 times on average, reduces the document retrieval latency down to 0.2% of the total latency of the RAG pipeline, and it also outperforms ND Search, a state-of-the-art design, by up to 2.5 times. So this was my talk, and I'll be happy to take any questions.